We're going to make use of the second translation theorem by finding the inverse Laplace transform of the quantity of 1 plus e to the negative 2s squared divided by s plus 2. There's not really a clever way to deal with this numerator other than expanding it, so we're going to go ahead and do that. This is the Laplace transform of 1 plus 2e to the negative 2s plus e to the negative 4s divided by s plus 2. We did that so that we could write this down as three separate fractions. The inverse Laplace transform of 1 over s plus 2 plus 2e to the negative 2s over s plus 2 plus e to the negative 4s over s plus 2. The inverse transform of 1 over s plus 2 is e to the negative 2t, no big deal there, plus 2 times, all right, let's look at the pieces here. The e to the negative 2s is going to inverse transform to the unit step function u of t minus 2. S plus 2 in that denominator would inverse transform us to e to the negative 2t. However, we need to make sure that the arguments in the unit step function and in the exponential match. So instead of e to the negative 2t, it's e to the negative 2 times the quantity of t minus 2. For the last term, again, we see the e to the negative 4s. That's going to give us the unit step function of t minus 4, e to the negative 2t, except the arguments t minus 4 need to match in both places, so it's e to the negative 2 times the quantity of t minus 4. Next, we have the inverse transform of e to the negative 2s divided by s squared times s minus 1. We need to perform partial fraction decomposition, but the fraction that we're decomposing is 1 over s squared times s minus 1. Let me write down what the decomposition looks like and then talk about a pretty major misunderstanding pitfall that I see sometimes. We have three fractions. Denominators are s squared, and s minus 1. And we have our, since they are all linear bases, even the s squared has a linear base, right? It's s with an exponent of 2. That means that our numerators are going to be constant. So we have a over s, b over s squared, and c over s minus 1. Let's think about what happens with partial fraction decomposition. The idea is I have these three algebraic fractions, and when I add them together, getting common denominators and everything, I end up with the fraction on the left. A major misunderstanding that I see sometimes is that people will put the e to the negative 2s in the numerator on the left. What's wrong with this? There's no way you're going to add a over s, b over s squared, and c over s minus 1 and in the numerator end up with an exponential. Doing that just shows a fundamental misunderstanding of what's going on with the partial fraction decomposition. An exponential absolutely never belongs in a partial fraction decomposition. We decompose it and then bring in a factor of e to the negative 2s. What that's going to look like, you can verify the work yourself, is the inverse transform of e to the negative 2s times the quantity of negative 1 over s minus 1 over s squared plus 1 over s minus 1. We have factored out the e to the negative 2s, and that actually makes it a little bit easier for us to write down the inverse transform here, u of t minus 2. And then the inverse transform of negative 1 over s is negative 1. No adjustment needs to be made to that thing. The inverse transform of negative 1 over s squared is negative t, but wait a minute, everywhere we write a t, we need to write down t minus 2. The inverse transform of 1 over s minus 1 is e to the t, but yes, again, that needs to be e to the t minus 2. If we had like a second term here, like, I don't know, plus 1 over s cubed or something like that, that would transform to 1/6 t squared. We would not put the t minus 2 in there if it wasn't being multiplied by the e to the negative 2s. Since that isn't what we had, I'm going to erase all that and leave it at that. This set of videos would really be incomplete without seeing the actual value of the unit step function in context. Use the Laplace transform to solve the initial value problem. Y prime plus y is equal to f of t, where f of t is the piecewise function 1 for t between 0 and 1, and negative 1 for t greater than or equal to 1. An initial condition is given y of 0 is equal to 0. The first thing we're going to do is express the forcing function f of t using the unit step function. In this case, it's going to be t minus 1 because that's the number where the piecewise definition for f changes. Now we've seen where the unit step function starts out off and then on and then on and then off, but not on and then on to something different. I'm going to write f of t as the sum of two separate piecewise functions because, why not complicate it even more? I'm going to say f of t is 1 or 0 to the left and right of intervals defined by t equals 1, plus 0 and then negative 1, again for intervals defined by t equals 1. Now in terms of the unit step function, when it's 1 and then 0, that's on and then off. The way we do that is 1 minus u of t minus 1. If this 1 were anything other than a 1, then I would have that duplicated in the first term and as the coefficient of the unit step function. For the part where it's off and then on, and when it turns on it's negative 1, that is negative 1 times the unit step function of t minus 1. We have some like terms. Combining that together, we get 1 minus 2 times the unit step function of t minus 1. As a quick little check to see that what we've done is correct, our f of t would equal 1 minus 0 for t between 0 and 1, that's when the unit step function is off, and then 1 minus 2 when t is greater than or equal to 1, and that's when the unit step function is on. Simplifying that, we see that that is 1 or negative 1, depending on where we are on the t-axis. That's exactly what it's supposed to be. The differential equation is then y prime plus y equals 1 minus 2 times the unit step function of t minus 1, and don't forget the initial condition, y of 0 is equal to 0. Now I want you to see if you can solve this equation and then come back. With y of 0 equal to 0, the transform of y prime is sy of s, and then plus y of s for the transform of y, and on the right hand side we have 1 transforms to 1 over s minus 2 times the unit step function t minus 1 gives us negative 2e to the negative s over s. Remember, the transform of 2 is 2 over s. Factoring in the left hand side gives us s plus 1 times y of s, and the right hand side is unchanged, and then dividing by s plus 1 gives us y of s is equal to 1 over s times the quantity of s plus 1 minus 2e to the negative s over s times the quantity of s plus 1. Notice I have completely separated the numerator that has the exponential with the numerator that doesn't. The fractions are basically the same. 1 over s times s plus 1 can be used in both of these decompositions. Just factor out the negative 2e to the negative s. We get that y of s is equal to 1 over s minus 1 over s plus 1 from the first fraction. With that minus 2e to the negative s factored out, we have that quantity times parentheses 1 over s minus 1 over s plus 1. The inverse transform of that equation gives us y of t is equal to 1 over s inverse transforms to 1, 1 over s plus 1 inverse transforms to e to the negative t, so we have 1 minus e to the negative t. Negative 2e to the negative s becomes negative 2u of t minus 1. All that times the inverse transform of 1 over s, which is 1, minus 1 over s plus 1. That plus 1 is going to give us a negative 1 in the exponent on the exponential, but then remember that everywhere I was going to write a t, I have to make it match the unit step function, and so that last term inside the bracket is e to the negative quantity t minus 1.